Hello everybody, in this video I will talk about absolute extrema, and let's start with the theorem for the functions of two variables. If f is continuous on a closed and bounded set D in R squared, then f attains an absolute maximum f of x1, y1 and the absolute minimum value at some points x1, y1 and x2, y2 in D, which means the existence of absolute minimum and the absolute maximum is guaranteed here. Okay, so because they exist, we can find using some methods. Okay, so to find them, we should follow the method I will write in a minute to find absolute max and absolute min of a continuous function on a closed interval, a closed and bounded set, first of all, we will find the values of f at the critical points. Of f in D, of course, not all the values. To do this, of course, first of all, we should calculate the we should find the critical points. The first step will be this: we will find the critical points, and then we will decide which of them in the given region. Then we will find the values of this function and critical points. Then we will find the extreme values of the function. Find the extreme values of the function of f on the boundary of D. Like in the single variable case. In the single variable case, we are given a function f of x and we are given a closed interval, if you remember. And we just try to find the absolute minimum or maximum of this function at on this interval, right? To do this, first of all, we find the critical points which belongs to this interval. And then we will we evaluate the value of the function at the point at the critical point belongs to this interval and at the end points of this function, and then compare the results, right? To find the absolute minimum or an absolute maximum in single variable, we use that method. So we use the same procedure here, but for this time we don't have a interval, we have a region. Because of that, we don't have endpoints, but we have boundaries here. Okay, so because of that, we will analyze the boundaries of the given region separately, and at the end, the largest of the values from steps 1 and 2 is the absolute max value, okay, and the smallest of the values from steps 1 and 2 is the absolute minimum value. Okay, so method is this: we know the existence, okay, we know that absolute mean and absolute max exist for the continuous function on a closed and bounded region. Then to find this, first of all, we will find the critical points, and we will find the critical points on the boundaries, and then we will evaluate our function at these points. Then we will compare the results, and the highest value, largest value, will be absolute max, smallest value will be absolute minimum. Okay, so let's solve problems. Again, step 1 is the finding the critical point. Okay, step 1. in the given region. So we want to find absolute max, absolute minimum of the function. First of all, we should talk about that, this function. And we have a rectangular region here. As you can see, this is a function as a polynomial, so it's continuous everywhere. And we have a region, it is a rectangle, it is bounded and closed. So because of the theorem, we can say that in this region, this function has absolute maximum and the absolute minimum. So to find this absolute maximum and the absolute minimum, we will first of all find the critical points in D, and then we will find the critical points on the boundary. Okay, so to do this, first of all, I will calculate the first partial derivatives. I have 2x minus 2y, and f sub y will be 0 minus 2x plus 2. So if you substitute, if you equate these first partial derivatives to 0, from the first equation I have x equals 1, y, and from second equation I have 2x is 2, which means x is 1. So if x is 1, because x equals y, right, y is also 1, which means I have 1, 1 as a critical point. And I have to check whether or not this point is in the given region. Okay, so as you can see, this region contains x's between 0 and 3, and 0 is less than or equal to 1, and 1 is less than or equal to 3. Okay, this is satisfying. And also y's between 0 and 2. So because y is 1 here, 0 is less than or equal to 1, and it is less than or equal to 2. So 1, 1 is a critical point in the given region. Okay, it means we will put this point on our table also. If it is, it won't be in the region here, then we won't put this point on our table to compare the results. Okay, so you should check the obtained critical point is in the region or not. Okay, let's continue with the second step. For this time, we will analyze the critical points on the boundary. Okay. Critical points or maximum, let me write it like that, max or minimum values. In other words, the local max or local maximum points of the function on the boundary. Okay, so I will first of all sketch the region. X is 0 means x is 0 here, and y is x is 3 is here. Because we have equalities, I use direct lines, not dashed lines. Y is 0 this x-axis, and y is 2 is here. Y is 2. So the region is this. Okay, we analyze the inside of the region, okay, the interior points, but it's time to use the boundaries. And as you can see, here we have 4 different sides of this rectangle. So because of that, we have 4 different boundaries. Okay, so boundaries are: first line is x is 0, second line is x is 3, okay, third line is y is 0, and fourth line is y is 2. The endpoints of the intervals gives the boundaries of the region. Okay, so I will use these boundaries to find the critical points on the boundaries. Okay, so let's start with the first line. On L1 we have x is 0. Okay. If x is 0, if you turn your function and the function is f of xy equals x squared minus 2xy plus 2y turns to, because x is 0 here, we have just a function depends on y. Okay, 0 minus 0 plus 2y, so I have 2y. It says that on this boundary here, on this line, my function can be calculated using only 2y. Okay, so because here 2y is an increasing function, and this equality holds for 0 is less than or equal to y and y is less than or equal to 2 here. On L1, here we have x is 0 and y is between these values because y changes between 0 and 2 in the given region. Okay, so here 0 and 2. So I have a function which is defined on this interval and it is increasing function. So the maximum value of f0y is, because it is increasing, it takes the maximum value at 2, f02, which is 4. Okay, and the minimum value of f0y is, for this time it takes the minimum value at 0 because it is increasing function, 0 0, so it is 0. Okay, we are looking for the maximum and the minimum values because we want to obtain the absolute maximum or absolute minimum. Okay, so on this line we have those values. So using the same idea, I will analyze the other boundaries also. Now on L2 we have x is 3 and again y is changing between 0 and 2. Okay, so my function turns to f of 3y. So I have 3 squared minus 2 times 3y plus 2y, which means we have 9 minus 6y plus 2y, and I have 9 minus 4y. Okay, and here y changes between 0 and 2. So I can say this, f of 3y equals 9 minus 4y is, for this time this is decreasing function. So the maximum value of f3y is, the maximum value for this time occur at the lowest end point because this is decreasing function, f of 3 0, and the f of 3 0 is 9. Just substitute 0 here, and the minimum value of this function is f of, it occurs when y is 2, f of 3 2. If you substitute 2 here, 9 minus 8 will be 1. Okay, so on this boundary we also obtained the needed results. Let's look at the next boundary on L3. On L3 we have y equals 0, but for this time, because y is constant, x changes between 0 and 3. Okay, so let's look at our function. I have f of x0 here. If y is 0, then this and this will be 0, so I have x squared only. Okay, so this function, x squared function, is an increasing function on this interval. Okay, on 0 is less than or equal to x and it is less than or equal to 3. Why? Because this is a parabola, right? On this side, this is decreasing function, but between 0 and 3, it is an increasing function. Okay. So because of that, maximum value occurs at the highest and largest endpoint, which is f of 3, 0, which is 9. Just substitute 3 here, and the minimum value of f of x0 is f of 0, 0, which is 0. Okay. We have one more boundary here, which is L4. On L4 we have y is 2 and x is between 0 and 3. Okay, so our function will be f of x2, x squared minus 2x2 plus 2 times 2, which means I have x squared minus 4x plus 4. Okay, so and we are on this interval, right? To decide it is increasing or decreasing, we can sketch the graph, but it will be a little bit difficult for us. But I can define a new function, okay, because this is, as you can see, this is a single valued function, right? Single variable function. So because of that, if I define g of x like that, g of x equals x squared minus 4x plus 4, okay, and if I take the interval as 0 and 3, now the problem in this step turns to find absolute max and absolute mean of g of x on 0, 3. The absolute extrema problem in single valued functions, right? So how can we do this? We can do this by finding first of all critical point of g, and then by calculating this function at the endpoints. Okay. Sometimes you can't decide whether or not the given function increasing, okay, or decreasing in the given interval on the boundary. So you have to use that method. If you substitute a constant for one variable, you will obtain a single variable function here. So because you have single variable function, you can use the method for finding the absolute extrema of the single valued functions on an interval. So g prime of x is 2x minus 4. If you equate it to 0, then you will obtain x is 2, right? So this is critical point of g, and we have x is 0 and x is 3 are end points of g. So in the table, we should consider these 3 points also. We have the values, values are g of 2, which is 2 squared minus 8 plus 4, which is minus 8, right? 2 squared is 2, which is 0 directly. So g of 2 is 0, g of 0 is 4, and g of 3 is 3 squared minus 12 plus 4, which is 9. Here we have plus 4 is 13, which is 1. Okay. There is no problem, right? I have... Okay. So it means if g of 2 is 0, actually g of 2 means x is 2 here, right? I will write it like that. F of x2 is g of 2, g of x, g of x. So g of 2 means f of 2, 2, and it is 0. And g of 0 means f of 0, 2, and it is 4. and g of 3 means f of 3, 2, and it is 1. Okay. So it's time to make a table. We have too many points here. First of all, I have 1, 1 as a critical point. Let's substitute it here directly. Step 3, chart or table. So I have 1, 1. Okay, first of all. This is the 1, 1 is the critical value in the domain, in the given region, sorry. And if you substitute 1, 1 here, 1 minus 2 plus 2, which is 1. F of 1, 1 is 1. Okay. And then on the first boundary L1, I have 2 points, 0, 2 and 0, 0. 0, 0, and we know that f of 0, 0 is 0, and I have 0, 2, so f of 0, 2 is 4. We obtained this here, okay? F of 0, 2, f of 0, 0. And on L2 here, I have 3 points, 2 points, 2, 0, and 3, 0, and 3, 2. So I will write it here, 3, 0, f of 3, 0 is 9, and 3, 2, and f of 3, 2 is 1. Okay. And here on the third boundary, I have 3, 0 and 0, 0. So I have 3, 0 here and 0, 0 here. There is no need to write them. And at the end, in the fourth boundary on L4, I have 3 different points, f of 2, 2, f of 0, 2, and f of 3, 2. We don't have 2, 2 here. Let's write 2, 2 here. F of 2, 2 is 0. Okay, this is written. 0, 2 here we have in the table, and 3, 2 we have in the table. So here we have x's, and here we have values of f of xy. So the possibilities here in the values of xy. So as you can see, this is the maximum value, 9, okay, in the table. And this is the minimum value, 0 and 0 in the table. So the conclusion is that the absolute minimum of f on D is f 0, 0. It occurs at 0, 0, or it occurs at here 2, 2, which is 0. And the absolute maximum of f on D is just occurs at one point, which is 3, 0, and the value is 9. Okay, the absolute maximum of the function is 9, and the absolute minimum value of this function is 0 on the given region.